Okay, let's see. Okay, well, thank you, everyone. It is a pleasure to have you all here in another session of this webinar. AmSur on differential geometry. And well, I would like to introduce our speaker today. It is Professor Giulia Dileo from Università degli Studi di Bari in Italy. Okay, well, thank you, Giulia. Go ahead.
Thank you very much. So I have to say, I only see my slides. So if you have questions, please talk. Well, thank you very much for the invitation in this seminar. Thank you especially to Adrian. I would like in this webinar to discuss the geometry of some special classes of transversely Kähler almost contact metric manifolds, focusing in particular on quasi-Sasakian manifolds and the new class of anti-quasi-Sasakian manifolds. This is a joint work with Dario Di Pinto from the University of Bari. So the context is the geometry of almost contact metric manifolds. So I will start with a brief introduction to this geometry. So what is an almost contact manifold? By an almost contact manifold, we mean an odd-dimensional manifold endowed with a geometric structure given by a 1-1 tensor field phi, vector field C, which we call characteristic of Rab vector field, and one from eta. This structure is such that the tangent bundle of the manifold splits into the sum of a line bundle spanned by C and an even subbundle, an even rank subbundle, defined as the kernel of the one from eta. This bundle, in fact, distribution coincides also with the image of the 1-1 tensor field phi, which vanishes on C and which induces a complex structure on D. Well, if M is an almost contact manifold on the product manifold of M and R, one can consider an almost complex structure J, defined in this way, and we say that the almost contact structure is normal if this almost complex structure J is integrable, which is also equivalent to the vanishing of the tensor field and phi defined by means of the knee-noise torsion of phi. Well, the normality condition can be equivalently expressed taking into account the complexification of the tangent bundle, which splits into the sum of the complex line bundle spanned by Xe and the two eigendistributions D10 and D01 corresponding to the eigenvalues I and minus I of the complex structure JD. And one can easily see that the normality condition for the almost contact structure is equivalent to require that D10 or also D01 is a Xe invariant involutive complex distribution. Well, an almost contact metric manifold is defined as an almost contact manifold which is endowed with a compatible Riemannian metric G, with respect to which the characteristic vector field C has a unit norm and is orthogonal to the horizontal distribution D. The fundamental 2 form associated to this structure is the 2 form here denoted by phi. And it is worth recalling that the monograph by Blair represents a comprehensive introduction to all these geometries. Here I'm recalling some remarkable classes of almost contact metric manifolds, which will be mentioned in the following and also used. First of all, contact metric manifolds are defined as almost contact metric manifolds such that the differential of the one form coincides with 2 times the fundamental 2 form. In which case, the one form eta is a contact form in the sense that this wedge product turns out to be a volume form. If furthermore the red vector field is scaling, the manifold is called a K-contact manifold. Sasakian manifolds represent a subclass of K-contact manifold. They are defined as normal contact metric manifolds. And here I'm recalling a well-known fact due to Boothby Wong on Sasakian manifolds. Namely, if the red vector field is regular with compact orbits, then the Sasakian manifold is the total space of a principal cycle bundle over a Kähler manifold, whose Kähler form defines an integral homology class. The one form eta of the structure is a connection form for the cycle bundle with curvature form given by the pullback of the Kähler form. And a special example is given by the odd-dimensional sphere as a hypersurface of C n plus 1, which fibers over the complex projective space of complex dimension n. Co-Kähler manifolds are another class of almost contact metric manifolds. They are defined as normal almost contact metric manifolds such that both the one form eta and the fundamental 2 form phi are closed. And in this case, the manifold is locally isometric to the remaining product of the real line and a Kähler manifold. Finally, we have a quasi-Sasakian manifolds, which include both Sasakian and co-Kähler manifolds, as they are defined as normal, almost contact metric manifolds with closed fundamental 2 form. Well, in general, for an almost contact metric manifold, this equation holds, providing the covariant derivative of the 1-1 tensor field phi with respect to the Levi-Civita connection, or equivalently of the fundamental 2 form. And in particular, co-Kähler manifolds are characterized by the parallelism with respect to the Levi-Civita connection of the fundamental 2 form, while Sasakian manifolds are characterized by this second equation. Well, in fact, the covariant derivative of the fundamental 2 form plays a central role in the classifying criterion of almost contact metric manifolds due to Chinea Gonzalez. Here I'm briefly recalling this criterion. Well, if we have a real vector space of odd dimension 2n plus 1 endowed with an almost contact metric structure, we can consider the finite dimensional vector space CV of all tensors of type 03 which have the same symmetries of the covariant derivative nabla phi. Well, Under the action of the group UN times 1, this vector space CV decomposes into the sum of 12 orthogonal irreducible subspaces, thus providing 2 to 12 invariant subspaces. And in particular, the null subspace corresponds to the class of co-Kähler manifolds. Well, I will deal with these 4 irreducible classes listed in this table with their defining conditions. But in particular, I will deal with these 3 reducible classes. C6 plus C7, which is known to coincide with the class of quasi-Sasakian manifolds, the class C10 plus C11, and the sum of these two. Well, regarding the sum of classes C6, C7, C10, and C11, we call manifolds belonging to this class generalized quasi-Sasakian manifolds. This notion was introduced by Christoph Bode in dimension 5. So we only extend this notion to any dimension. And these manifolds are characterized by these 3 conditions, that is, the Reb vector field the C should be killing, and both the differential of the fundamental two-form phi and the 0,3 tensor field defined by n phi vanish on horizontal vector fields x, y, and z. Well, the fact that the Reb vector field C is killing implies that the Riemannian metric is projectable along the one-dimensional distribution spanned by C. In general, in this class, the 1-1 tensor field phi is not projectable. But if we also assume that the Lie derivative of phi with respect to Xi vanishes, then both G and phi are projectable, so that these manifolds admit a local Riemannian summation onto an even-dimensional Riemannian manifold, which is in fact a Kähler manifold. And for this reason, we call these manifolds transversely Kähler almost contact metric manifolds. Well, quasi-Sasakian manifolds are a subclass of transversely Kähler almost contact metric manifolds. In general, in an almost contact metric manifold, these identities hold, which in particular, assuming the structure to be quasi-Sasakian, imply that both the Lie derivatives of G and phi with respect to Xi vanish. But for a quasi-Sasakian manifold, we can say something more, as the two form given by the differential of the one form eta is also projectable, and the normality of the structure implies that this two form is phi invariant. So, taking into account the local Riemannian summation of the manifold onto a Kähler manifold, the two-form d eta projects onto a closed two-form of type 1,1. For a quasi-Sasakian manifold, we say that the structure has constant rank to R plus 1 if pointwise we have these identities. And in particular, co-Kähler manifolds have minimal rank 1, while Sasakian manifolds are quasi-Sasakian manifolds of maximal rank to n plus 1. The fact that the vector field C is in the kernel of the two-form d eta means that the structure cannot have even rank. Well, here I recall a research due to Kanemaki characterizing quasi-Sasakian manifolds as almost contact metric manifolds for which there exists a 1-1 tensor field A, which is symmetric and commutes with phi, and such that the covariant derivative of phi with respect to nabla is given by this equation. Well, our objective at this point is to define a new class of transversely Kähler, almost contact metric manifolds, such that the transverse geometry with respect to Xi is given by a Kähler structure which is endowed with a closed-to form of type 2-0. And by a closed-to form of type 2-0, we mean a giant invariant to form, since, as it is well known, on a Kähler manifold, but in general on a complex manifold, there's a one-to-one correspondence between closed complex two forms of type 2-0 and closed real two forms which are giant invariant. And in particular, in the non-degenerate case, this is nothing but a complex symplectic structure. The dimension of the manifold in that case is a multiple of 4. Well, a well-known example of Kähler manifolds endowed with a complex symplectic structure is given by hyperkähler manifolds. Well, an hyperkähler manifold is defined as a 4n-dimensional Riemannian manifold endowed with 3 almost complex, compatible almost complex structures which satisfy quaternionic identities, and such that the 3 almost Hermitian structures are all Kähler. In fact, by a result of Itchin, we know that if the 3 fundamental two forms associated to the 3 almost Hermitian structures are closed, then the manifold is necessarily hyperkähler. And in particular, we know that it is Ricci flat. In particular, if one chooses a Kähler form, then the complex two-form omega c defined in this way is a non-degenerate closed form of type 2-0. And by a result of Beauville, we also know that compact Kähler manifolds endowed with non-degenerate closed 2-0 form always admit a hyperkähler metric. Well, in order to define this new class of almost contact of transversely Kähler almost contact metric manifolds, we need to modify the normality condition. And we introduce this notion of antinormal almost contact structure, which is simply defined by requiring the tensor field n phi given by this equation. This, in particular, implies that the Lie derivatives of eta, d eta, and phi with respect to xi vanish, and the two form given by the differential of eta is phi anti-invariant. Hence, if we consider the local summation of m on the quotient of m over xi, we have that the 1-1 tensor field phi projects onto an almost complex structure J, which turns out to be integrable. And also the two-form d eta projects onto a closed two-form of type 2-0. In the special case where eta is a contact form, then this induced two-form is a complex symplectic structure on the base space. Otherwise, in the general case, we can always consider a phi invariant distribution, here denoted by E, and when this phi invariant distribution has even constant even rank, then the dimension of the manifold is of type 2q plus 4p plus 1, and in particular we say that the antinormal structure has rank 4p plus 1. Well, as for normality, we can consider the complexification of the tangent bundle, and we can characterize the antinormality in terms of the eigendistributions d10 and d01 of the complex structure defined on the horizontal distribution. Well, obviously, if we consider the almost complex structure J defined on the product of M and R, this is no more integrable, and in fact, the rank of the structure measures the non-integrability of the almost complex structure. Well, let us consider now a compatible Riemannian metric. Well, if we consider a compatible Riemannian metric, an almost contact metric manifold is said to be an anti-quasi-Sasakian manifold if it is antinormal and it has a closed fundamental two form. And this in particular, we show that anti-quasi-Sasakian manifolds are transversely Kähler almost contact metric manifolds. And if we consider the local Riemannian summation onto the Kähler manifold M over Xi, the two-form d eta projects onto a closed two-form of type 2, 0. Obviously, a normous contact metric manifold is both quasi-Sasakian and anti-quasi-Sasakian if and only if it is co-Kähler. As a consequence, we have a Booth-Wang type theorem in the sense that if Xi is regular with the compact orbits, then the manifold is the total space of a principal cycle bundle of a Kähler manifold which is endowed with a closed to form of type 2, 0. The one form eta is a connection form whose curvature form is exactly the pullback of this two form omega. And conversely, we can start by considering a Kähler manifold endowed with a closed two form of type 2, 0, defining an integral cohomology class, and then we can show that there exists a principal cycle bundle over B and a connection form such that the curvature form is given by the pullback of the two form omega, and the total space M is endowed with an anti-quasi-Sasakian structure.
Can I ask a question?
Yes.
Hi. So about the previous slide.
Yes.
It's just typically, or in the Sasakian case, the base manifold, the sort of leaf space of this foliation is singular, right? And there's no reason why it should be a smooth manifold. So I just want to know if you mean by Kähler manifold, this is really an orbifold picture, or is this a sort of strictly smooth kind of result?
So here we are assuming regularity. So if you don't assume a regularity, you on the base manifold, you don't have a manifold, a smooth manifold.
Well, but there are regular Sasakian fibrations with orbifold base space, aren't there? Like a weighted projective space, take some, you know.
Okay.
So I think maybe at the very least, this theory may be expanded a little bit, because whatever you proved here is probably right if the base manifold is actually a Kähler orbifold, which is a good thing, I guess.
Okay, thank you very much.
Cool.
Okay. Well, as an example, we can apply it to a Kähler manifold of a real dimension for n, and at least locally on a coordinate neighborhood, we can one can always consider exact forms of type 2-0 and rank 4p. So that on the trivial cycle bundle, one can define in a natural way an anti-quasi-Sasakian structure. And in particular, this can be applied to the unit disk of complex dimension to n, endowed with the Kähler structure of constant negative holomorphic sectional curvature. Well, here there is an analogous of Kanemachi result for quasi-Sasakian manifolds, providing a characterization of anti-quasi-Sasakian manifolds by the existence of a 1-1 tensor field A, which is skew-symmetric and anti-commutes with phi. And such that the covariant derivative is given by this equation. In this case, differently from the quasi-Sasakian case, the tensor field phi is uniquely determined. And using this result, we can clarify the placing of these manifolds in the Chinea-Gonzalez classification, since we can show that anti-quasi-Sasakian manifolds are exactly all manifolds in the class C10 plus C11, such that the Lie derivative of phi with respect to xi is equal to 0. So this picture summarizes all the classes involved in this discussion. We started with generalized quasi-Sasakian manifolds. If one assumes the structure phi to be projectable, we have the class of transversely Kähler almost contact metric manifolds. And inside this class, quasi-Sasakian manifolds are characterized by the phi invariance of the two-form d eta. Anti-quasi-Sasakian manifolds are characterized by the phi anti-invariance. I have to say that anti-quasi-Sasakian manifolds cannot be of pure class C10 nor of pure class C11. Well, a special type of anti-quasi-Sasakian manifolds is given by manifolds with a transverse hyperkähler structure. So let us consider a Riemannian manifold endowed with three compatible almost contact structures sharing the same vector field xi, and such that they satisfy these quaternionic type identities. So that the structure group of the manifold is reducible to S1, and the dimension of the manifold is 4n plus 1. We call these manifolds all SPN almost contact metric manifolds. And for this structure, we can show that this equation holds, which in particular says that if it happens that the fundamental two forms of the three structures are all closed, then this vector field and phi xy has no horizontal component. So let us assume that three structures satisfy these three equations. In particular, the first two fundamental two forms are closed, while we're assuming that the third structure is contact metric. But the three fundamental two forms are all closed. As regards the vertical component of the vector fields and phi xy, this, in this case, is given, depends on the third fundamental two form. And the quaternionic identities imply that this fundamental two form phi3 is invariant with respect to the structure phi3 anti-invariant with respect to the other two structures, so that the first structure is normal, the first one and the second one are anti-normal. And in particular, the third almost contact metric structure is quasi-Sasakian. The first one and the second one are anti-quasi-Sasakian. We call these structures double AQS Sasakian structure. In particular, they are transversely hyperkähler. And I have to say that in the special case of n equal to 1, that is the fine dimensional case, this structure has a special type of key contact type of SU2 structures. Here there is an example. This is a two-step nilpotent Lie group, which we call White-Heisenberg Lie group, whose Lie algebra of dimension for n plus 1 has these non-vanishing commutators depending on some real numbers, lambda 1, lambda n. And on this Lie group, we can define in a natural manner a left invariant SPN almost contact metric structure, for which the fundamental two forms phi I and the differential of the one form eta are given by these equations. And in particular, for this Lie group, we have that the first two structures are anti-quasi-Sasakian. The third one, in general, is quasi-Sasakian. In the special case, where the coefficients lambda 1, lambda n are all equal to 1, this is nothing but the real Heisenberg Lie algebra of dimension for n plus 1 with Sasakian structure phi3 xi eta g. And in this case, this is in fact a double AQS Sasakian structure. Being a two-step nilpotent Lie group by a result of Malchev, if these coefficients are rational numbers, then the manifold, the group admits a compact discrete subgroups, so that we can consider induce analogous structures on the compact Lie manifold given by the quotient. Well, I want to focus now on the curvature of these manifolds. Well, if we consider a double AQS Sasakian structure, since we have a Sasakian structure as it is well known, the C-sectional curvatures, that is sectional curvatures of two planes containing the direction of C, are all equal to 1. And in fact, we can show that double AQS Sasakian manifolds provide all anti-quasi-Sasakian manifolds with constant C-sectional curvatures equal to 1. In order to show this, we need some technical facts. First of all, considering in general an anti-quasi-Sasakian manifold, we can consider the already introduced operator A and the operator Psi, which is given by the opposite of the covariant derivative of Xi. These are both skew-symmetric and satisfy these identities, which look like quaternionic identities, but actually A and Psi in general do not define almost contact structures. Since A and Psi are skew-symmetric, we can consider the associated two forms. So in total, we have two forms which are all closed and in fact satisfy these equations. The fact that A is closed is not really immediate, but it can be shown. Well, in particular, the manifold is co-Kähler if and only if the operator Psi is closed, while the operator Psi square, which coincides with a square, is symmetric with non-positive eigenfunctions. Well, by the fact that in this structure the Reb vector field is killing by a standard argument, we have that the C-sectional curvatures are always non-negative. And in particular, you can see that the C-sectional curvatures are all equal to 0 if and only if the operator psi vanishes, which means that the structure is co-Kähler. But let us assume that the C-sectional curvatures are all equal to 1, in which case the spectrum of psi square or a square is 0 minus 1 with a 0 simple eigenvalue. Well, in this case, both psi and a satisfy are define almost contact structures. The fact that A and C are skew-symmetric imply that these two structures are compatible with the Riemannian metric G. And if we go back to the previous slides, considering equations 1 and 2, equation 1 implies that we have an SPN almost contact metric structure. Equation 2 says that this is a double AQS Sasakian structure, since we have the first two structures to have closed the fundamental 2-4, and the third one is contact metric. So we have showed that all anti-quasi-Sasakian manifolds with a constant C-sectional curvature 1 are double AQS Sasakian. In particular, being double AQS Sasakian, they are transversely Ricci flat. And we can say something more on the Riemannian Ricci curvature, since in general, for an anti-quasi-Sasakian manifold, we can show these identities on the Riemannian Ricci curvature. In particular, the third equation establishes a relation between the Ricci curvature of the anti-quasi-Sasakian manifold and the Ricci curvature of the Kähler base space. We can also have a relation between the scalar curvatures of the two manifolds. Well, this has various consequences. First of all, let us assume that the C-sectional curvatures are all are equal to a negative constant real number. Well, we can apply a special homothetic deformation of the structure and recover a double AQS Sasakian structure, so that being the two matrices G and G prime homothetic, they are both transversely Ricci flat, and applying our equations on the Riemannian Ricci curvature, we can have a complete expression of the Ricci curvature of our structure, which in particular says that the almost contact metric structure is eta Einstein. Well, in particular, this allows to show that if an anti-quasi-Sasakian manifold have a constant sectional curvature K, then it is necessarily flat and co-Kähler. And this is quite immediate, because if we assume the sectional curvature to be constant, then we have a constant C-sectional curvatures. And if this K is non-zero, as we have seen, the manifold is eta Einstein, non-Einstein. So necessarily this K has to be 0, which implies that the operator psi vanishes, and this means that the manifold is co-Kähler. Here there are some other obstructions to the existence of anti-quasi-Sasakian structures, in particular in the compact regular case. Well, if we assume that the anti-quasi-Sasakian manifold is a compact regular non-co-Kähler, then the Kähler base space is a compact Kähler manifold with a non-vanishing closed to 0 form. And thus, we know that the manifold cannot have positive definite Riemannian Ricci tensor. But if we consider our relation between the two Ricci curvatures, this exactly happens either if the Ricci tensor field of M is positive definite, or if it is non-negative and the structure is of maximal rank. Well, finally, I would like to treat this aspect. Well, if we take an anti-quasi-Sasakian manifold and a Kähler manifold, on the product manifold, in a natural manner, we can define an anti-quasi-Sasakian structure, preserving the rank. At this point, it is natural to ask whether starting with an anti-quasi-Sasakian manifold, this is decomposable as the Riemannian product of an anti-quasi-Sasakian manifold of maximal rank or a Kähler manifold. Well, it can happen under some suitable hypotheses. And in order to show this, we need a special metric connection adapted to the structure. We show that, given an anti-quasi-Sasakian manifold, there always exists a metric connection which parallelizes all the structural tensor fields, and such that the torsion is totally skew-symmetric on the horizontal distribution and vanishes along C. This connection, which we call canonical, is uniquely determined. It is the difference between this connection and the Levi-Civita connection is given by this H, and the torsion is simply given by the tensor product of the eta and Xi. In the special case where we have a double AQS Sasakian manifold, so the special case where the third structure is Sasakian, this connection coincides with the Tanaka-Webster connection of the Sasakian structure. Well, now if we consider an anti-quasi-Sasakian manifold and assume that the operator Psi is parallel with respect to the canonical connection, this is also equivalent to require that this canonical connection has a parallel torsion. Then we can consider two complementary orthogonal distributions which turn out to be integrable with totally geodesic leaves, so that the manifold is locally isometric to the Riemannian product of an even dimensional manifold tangent to the first distribution and a manifold of dimension for p plus 1 tangent to the second distribution. On the first on each leaf of the first distribution, one induces a Kähler structure. On each leaf of the second distribution, we have an anti-quasi-Sasakian structure of maximal rank. And if furthermore we assume that the manifold is connected, then the operator Psi square has constant eigenvalues, so that considering a non-vanishing eigenvalue, then the distribution spanned by Xi and the eigenvectors corresponding to this eigenvalue is always integrable with totally geodesic leaves, and each leaf up to a homothetic deformation is endowed with a double QS structure. But as a consequence, we have a further obstruction. That is, we can show that there exists no connected locally symmetric non-Kähler anti-quasi-Sasakian manifolds such that the operator psi is parallel with respect to the canonical connection. Why this happen? First of all, a double AQS manifold cannot be locally symmetric. This is because in a double AQS manifold we have a Sasakian structure, and by a well-known result due to Okumura, we know that locally symmetric Sasakian manifold have constant sectional curvature 1. But we know that this is not possible for double AQS manifolds. Well, if we consider, as a second step, if we consider a locally symmetric non-Kähler anti-quasi-Sasakian manifold such that psi is parallel with respect to the canonical connection, then we can consider a non-zero constant eigenvalue mi, and each leaf of the distribution spanned by xi and the eigenvectors with the eigenvalue mi is endowed with an anti-quasi, up to a homothetic deformation is endowed with a double AQS structure. But being totally geodesic, it remains locally symmetric, and this is not possible by the first step. Well, maybe I was too quick. This is a short bibliography, and thank you very much.
Okay, thank you, Giulia, for this very nice talk. Okay, okay, I have some comments there. Are there any questions or comments? Enrique?
Hi, can you hear me?
Yes, yes.
Yes.
I think Dario was first.
I don't. Dario?
No, I pressed the wrong button. Sorry.
Okay. Don't worry.
So, Giulia, one way to think about, say, typical Sasakian geometry is that the fact that the cone over them is scalar, right?
Yes.
So what kind of conical geometry can we see over these quasi, these sort of flexibilizations of Sasakian geometry?
We didn't look very much to the geometry of the Kähler cone. We mainly focused on the transverse geometry. But yes, can be investigated. Yeah.
Yeah, and so my maybe expanding a second on the question during the talk is if you take, for instance, weighted projective spaces, they are singular. They're typically singular Kähler manifolds, Kähler orbifolds, and they have, well, typically also natural Hopf vibrations over them coming from a higher dimensional sphere. So even though the Sasakian vibration is regular, all of the fibers are smooth circles, compact circles. The total space is smooth, even though the leaf space is not. Several of the theorems you proved could perhaps have a stronger version, perhaps even with the same proof, in this sort of more general, still regular Sasakian context. That's the point I was trying to make.
Yeah.
Your results are at least as good as you present them, but they could be a little more. They could be a little stronger for the same price. So if you have a look at that, I think that could be interesting.
Okay, thank you very much. Yes.
Cool.
Okay, Diego Conti has one question. Diego? Hi, Diego. Do you want to ask a question?
I think Diego is muted, is he?
Yes, probably. And now? Hi, Diego. Oops.
Oh, well. Shame.
So, doesn't work.
Okay. But perhaps I can ask one small question. Have you looked for more examples of these structures on Lie groups apart from these Heisenberg?
Well, we don't think there are many Lie groups.
Okay, do you have some abstractions or?
Well, we looked for some more, but yes, still in the homogeneous there are some structures, because I didn't mention, but if you apply, I mentioned this result on compact regular, no? Well, if you assume the homogeneity, if you take a homogeneous antiquasi-Sasakian manifold, then this cannot be assuming. At least we need this assumption on the Ricci curvature. This is also an abstraction, since for homogeneous contact structure they are always regular. So you apply the already mentioned result. And for Lie groups, well, maybe there are not a lot Lie groups,
Okay.
but we need some further investigation on that.
Okay, good, good. Thank you. Okay, then are there any other questions for Giulia? No? Okay, if this is not the case, let's thank Giulia again.
Thank you for the invitation.